Continuing on integration of functions of a complex variable, let's look at the Cauchy-Goursat theorem. Okay, here's where we left off in section 44. We saw that if the integrand f is continuous throughout some domain D, has an antiderivative on that domain D, then the integral about contour C of f of z dz is 0 if C is any closed contour in D. Okay, so we're often going to see this type of behavior. This isn't a terribly constraining condition that we have a continuous integrand and then has an antiderivative. Most of the quick functions you'll rattle off satisfy that. Polynomials satisfy that. Sines and cosines, exponentials. Might get into some trouble once we start doing things with logarithms, as foreshadowed in the conversations, because here comes those branch cuts. Then we got potentially some problems. All right, so in this section, we state a result giving some other conditions on function f that guarantees that such integrals will be 0. So we're going into this requiring f is continuous and has an antiderivative. All right, so one little observation to get the ball rolling, one lengthy observation actually. Suppose C is a contour given parametrically by z of t, t ranging from a to b. Then we've defined the integral about c of f of z dz to be an integral from a to b of f of z of t, z prime of t dt. That's our very definition of contour integral. Okay, if we'll write f in terms of its real and imaginary parts, u of xy plus iv of xy, as we've done many times, and take z of t, the contour, write it as x of t plus iy of t, so we're breaking it into real and imaginary parts. Remember, z prime is something complex, f is something complex, so we're just breaking the f's and the z's into their real and imaginary parts. Then, if we want to expand this up here, we're going to be messy in the short term. We're going to take c of t and put it inside of the f function. That's putting x of t plus iy of t in for z of t. So u of xy becomes u of x of t, y of t, plus iv of xy plus iv of x of t, y of t. And then the z prime stuff includes some x prime plus iy prime of t stuff. So we got a little product here, FOIL it. That produces all of this stuff here. Trust me on the arithmetic. Let me just make an observation. There's a negative sign. Yeah, came from when that I there and that I there got together. So that's where that particular negative sign comes from. Let's suppress some of this of t stuff and just write u's and v's and x primes and y primes. So getting rid of all the of t stuff, we can simplify it down to something that looks like this. The prime would have to indicate derivatives with respect to t, because that's the types of derivatives we were talking about with the x's and the y's, and the x primes and the y primes. Okay, let's do a change of variables. Looking at the differential relationship, dx equals x prime of t dt, that's the very definition of dx and dt when we've got x as a function of t. Similarly, dy is y prime dt. Never liked differentials myself, but that's the specific meaning of those. Really what's happening here is we're going through some chain rule stuff and some change of variables, but anyhow. Let's swap the x prime dt for dx. So we'll have an integral of u dx, x prime of t dt becomes dx. Here's another x prime of t dt, so it's an integral of v dx. And similarly, y prime dt, replace those with dy's. Okay, so we can rewrite this original integral, the original contour integral, in terms of these types of integrals here. Let's shift gears briefly. We're going to come back to this. And what we've accomplished is, we ain't accomplished anything. We've changed this integral in terms of f of z's, dz's, and written it in terms of this other stuff. in terms of integrals with respect to x and y. Well, the reason we wanted to do that is to borrow the following result from vector calculus, the notes say. All right. Let me just point out to motivate even looking at this. See down here in Green's theorem, we've got a function dx plus a function dy, and we're integrating something dx, something dy. That's what we got up top. We got an integral, and it's going to disappear. We got an integral of something dx and something dy. Something dx, something dy. So both of these integrals on the right-hand side of equation 3, they look like this stuff. So that's why we're looking at Green's theorem. So we're going to take Green's theorem. It's going to move us from the setting of complex integrals into a setting of double integrals in the real setting. So you saw this in Calculus 3, because that's where you do double integrals. Yeah, probably not. When I do Calculus 3, we don't do the vector calculus stuff. We're too busy doing other stuff. Maybe in an applied math class, you'd run across Green's theorem. It's in the calculus book, but probably you didn't have a time to cover this content from the calculus book. If you did, it would have been Calculus 3. All right, so the statement of Green's theorem is that P of xy and Q of xy be continuous, and suppose each of the first partial derivatives of P and Q are continuous. So there's some continuity condition on partial derivatives, first partial derivatives, which will relate to f prime for us shortly. Throughout this closed region R, consisting of all points interior to and on simple closed contours C. All right, we're doing something a little bit shady here. We're going from C, originally given as a simple closed contour in the complex plane. Here we're dealing with the Cartesian plane, the xy plane, where everything's real. Well, we're doing the obvious association of complex numbers with pairs of real numbers. So this simple closed contour has become now a contour in the Cartesian plane, not the complex plane. That's mostly a technicality. And Green's theorem claims that we can write that as a double integral over the region R, as described. It's the contour and the points inside it. Partial of Q with respect to x minus partial of P with respect to I, and then a dx dy, a differential of area. Okay, so as observed, we're going to use that to rewrite where we left off upstairs. All right. If we have f analytic in a region R, okay, now I'm going the other way. I'm taking this region R from R2 and pretending it's a region in the complex plane. That's not a surprising thing to do, but worthy of pointing out. If f is analytic, then it's differentiable, and that was mostly the definition that we had of analytic. If the derivative f prime is continuous on R, then the first order partial derivatives of u and v are continuous because we had f prime expressed in terms of first partials of u and v. Back when we showed the Cauchy-Riemann equations, implied differentiability with the continuity part thrown in. So we had seen this before when we expressed derivatives in terms of these. To get, if we have differentiability, then we have the Cauchy-Riemann equations. This theorem 2.22a went in the other direction. If you have the Cauchy-Riemann equations and you have continuity of first partials, then you have differentiability. So then we can take what we had in equation 3 and rewrite it in this form. So let's see, we've taken equation 3, we left off with this u dx minus v du stuff. Yeah, here that is. So here is equation 3 rewritten. Now we're going to use Green's theorem. So it's a hole in our knowledge. We didn't prove Green's theorem, but we're taking that as given. We need a little bit of stuff from advanced calculus. We've done this before, borrowed some things from advanced calculus. We borrowed some subtle things from topology too. So we're going to take these types of integrals, here we've got a u dx minus v dy. All right, well, that can be rewritten in terms of partial derivatives. So we'll take the p of x, which we're treating as a u, and replace it with, let's see, goes over here on the right-hand side, a partial of that with respect to y. So we'll take the u, partial of u with respect to y, it goes over here on the right-hand side with a negative sign in front of it, is given right there. This part for us is negative v. We got a negative v where the q is. So we'll take a partial of that with respect to x. That'd be negative v sub x. Okay. And then similarly for the other part. All right, leaving us with equation 4. Let me keep you in suspense for a second. All right, down there in equation 4, we're trying to show, remember what the big picture is, we're trying to show this integral 0. We're integrating a nice function around a simple closed curve. We ought to get zeros out if it's that nice. We got analytic everywhere, we ought to get 0 out for sure. Okay, so I want to show that equation 4 implies integrals of 0. One piece of information we haven't directly used is Cauchy-Riemann equations. We referred to them up here, knowing that first order partials are continuous, but we never use specifically u sub x equals v sub y and u sub y equals negative v sub x. We haven't used these equations, the Cauchy-Riemann equations, just yet. Let's use them now. So let's see, the u sub y, u sub y is negative v sub x. So let's plug negative v sub x in for u sub y. Here you go. And let's do a similar type thing for u sub x. U sub x is v sub y. Let's make that substitution. So I've taken equation 4. The two terms here with extra parentheses around them have been substitutions based on the Cauchy-Riemann equations. They're good substitutions because negative v sub x minus negative v sub x is 0. V sub y minus v sub y is 0. Both of these got integrands as 0. So the integral is 0. So when f is analytic on R, we needed that. When f prime is continuous, where'd we use that? F prime is continuous. It's when we use Green's theorem. Remember, it required these p's and q's to be continuous, the first partial derivatives of the p's and q's to be continuous. For us, that was requiring that the u's and v's have continuous first partials. And f prime is written in terms of first partials of u's and v's a couple of different ways, as we saw, whoops, right there at the top of the screen. So we've got continuity of these. That allows us to go through and use Green's theorem. And when we have an analytic function with a continuous derivative, all right, so this is different from what we had in the previous section, then we get an integral of 0. In the previous section, we talked about analytic functions, which I talked about continuous functions, actually. Continuous functions with antiderivatives. There's no mention of antiderivatives in this. There's a requirement of continuity of the derivative, but nothing about antiderivatives. Okay. That, it turns out, requiring analytic function with continuous derivative, that can even be further softened, and was done so by Koshigerosa. He was the first to prove that the condition that continuity of f prime can be removed, and all we would require then is that f is analytic on R. Okay, that hides a little bit of stuff there. We need f to be analytic on and inside simple closed contour C. Then we'll get an integral out of 0. That'll be the Koshigerosa theorem. So Koshigerosa is the first to prove that we don't need to look at f prime. We don't need to look at antiderivatives or f prime. We can just look at the function of f itself, and if it's analytic on and inside simple closed contour C, then we'll get out integrals of 0. If we had a little bit more knowledge about analytic functions, this wouldn't be terribly surprising. For us, analytic functions are functions that are differentiable on open neighborhoods, open regions. Yeah, it turns out Analytic functions have power series representations. You want to take that out of this class. Analytic means power series representation. We may not have time to get to the power series stuff here in chapter 5, but if we did, we'd see that analytic functions have power series representations, and power series representations are representations of analytic functions. So we're getting analytic if and only if power series before we're done, ideally. And when you take a real analysis class, analytic is going to mean power series representation. So even though we started with a different definition of analytic, you think analytic means power series representation, because that's what it's equivalent to. It's, in some sense, it's just the way the book's laid out. It's the way all complex analysis books are laid out. We've taken a slightly different approach to analytic than the graduate text we use takes, but anyhow, it doesn't say anything about power series initially either. In the end, analytic means power series representation in the real setting. In the complex setting, when you hear the word analytic function, you think power series. Okay, so here's what we get for the Cauchy-Goursat theorem. If f is analytic at all points interior to and on a simple closed contour C, then integrals of f about that contour are 0. Okay, so that would be probably fairly easy to check. I mean, to check for analytic, all we have to do is check and see if the derivative exists, the function exists, and its derivative exists. I can immediately think of some functions to which this applies: polynomial functions, exponential functions, sines and cosines, products of those things. I can think of some things it doesn't apply to as well. Doesn't apply to 1 over z. 1 over z is not analytic at 0. 1 over z had some weird behavior. It doesn't apply to 1 over z squared. It's not defined at 0 either. There's no branch cut for 1 over z squared. I know, go looking for antiderivatives. It's 1 over z doesn't have a branch cut either, but it's antiderivative. Some branch of the logarithm does. 1 over z squared, I can't use this because 1 over z squared is not analytic at 0. If we take a contour about 0, I can't use this. Yet, we still had, if I put 1 over z squared there and c, say, as a unit circle, positively oriented, we did get an integral of 0. Not because of the Cauchy-Goursat theorem. It doesn't apply to 1 over z squared because z equals 0 is a problem if that's interior to contour C. If it's not, then we're good to go. But we've seen functions to which this applies, and we've seen some functions where we got integrals of 0, but not because of the Cauchy-Goursat theorem. And we've seen functions around closed contours that don't give 0 as well. A quick little bit of history on this Goursat dude. Big name in analysis in the late 19th century, the late 1800s. I guess he was active in the 20th century as well, but I'd place this guy really more as a 19th century mathematician. He's influenced by Picard, Darboux, Hermite. Picard from Picard iterates and differential equations. Darboux sums you might see in analysis. Hermitian matrices you might run across in a somewhat like a second matrix theory class, probably not in linear algebra. Might be buried somewhere in the exercises, but probably you don't see Hermite so much in linear algebra. But he is a matrix theory guy. So these are all big name folks. And I stuck the history in here because what we're looking at here and what you look at in senior level real analysis, it's really the analysis of the 1800s. It starts with Cauchy, and Cauchy's got his name all over all this complex stuff. He's got his name over a fair amount of that real stuff as well. The analysis you study as an undergraduate is the analysis of the 1800s. Much of it is the analysis of Cauchy. Cauchy's the guy that thought you ought to look at epsilons and deltas. He's the guy that gives the epsilon delta definitions. And Cauchy's the guy that really puts analysis on, or puts calculus on a more rigorous foundation. The calculus of Newton and some of those pre-1800 folks, it was a little sloppy. By modern standards, it was certainly sloppy. Cauchy's the one that puts rigor into calculus, and he's the guy that brings you all this analysis stuff. In fact, Cauchy wrote the first thing that would be considered a calculus book, calculus textbook. I mean, Newton wrote a book on calculus, but you definitely wouldn't want to try to learn calculus from it. But Cauchy writes the first real calculus textbook in about 1800. Speaking of Goursat, he publishes a paper, some little trivia about Goursat in addition to his connections to this integral stuff and this complex stuff. Published a book in 1884. Where, let's see, maybe it's not that book. He publishes a book, Course in Analysis, and Analytic Mathematics, I guess is how you translate this. He starts referring to L'Hopital's rule as L'Hopital's rule. Maybe other folks thought of L'Hopital's rule before L'Hopital, but the rule we call L'Hopital's rule today, we call it that because of one of Goursat's publications, one of his books. The result about indeterminate forms and limits of indeterminate forms. These little hodgepodge of historical notes come from the Mac Tudor History of Mathematics Archive. Here's your picture of Goursat. There's an exceptional reference out there, this Mac Tudor History of Math thing. Loads of history, biographies of these folks, well into the 20th century. You take a history of math course and you probably don't get to very modern stuff. You probably get to calculus and that's about it. It concentrates a lot on ancient Greek mathematics. But this is a very exhaustive collection of stuff on biographies, particular topics. The fundamental theorem of algebra has a page devoted to it. Individual topics have lots of material devoted to individual topics on the Mac Tudor History of Mathematics Archive. Seeing things in a historical context kind of makes it make a little bit more sense. Who did what and when and why? And one thing we don't see much of in this class is, a lot of this stuff, it was inspired by applied problems, and some of that spelled out in the historical record. So that takes care of Cauchy-Goursat theorem. We need to do a little bit more stuff on integration. We need to get to the Cauchy's integral formula, which is intimately related to the development of power series. We may not have time to get to power series, but we got to get through the Cauchy's integral formula stuff. I'll see you next time.